All right, in today's lesson, we're going to look at numeration systems. Basically, how have different cultures handled numbers, and then how do we translate it into something that we can understand. So our first definition is we're going to start with this idea of what a numeral is. Okay, numerals are written symbols to represent cardinal numbers. Okay, so you got to think for a second, what are cardinal numbers? Cardinal numbers are what we consider to be the counting numbers. So how many of an object? There's 1, 2, 3. Those referred to as cardinal numbers. Okay, a numeration system, let me write that out. Okay, a numeration system is a collection of properties and symbols agreed upon to represent numbers systematically. In other words, the rules that dictate how we document numbers we refer to as a numeration system. That's pretty straightforward. The one that we are the most familiar with is the Hindu-Arabic numeric system. And this is where all numbers are constructed from 10 digits. And place value is based on powers of 10. Okay, so let me just remind us when we say digits, we mean 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of our numbers and what we consider to be in our system are derived from those 10 symbols. Believe it or not, those are symbols. And we let place value dictate whether or not a number, what the number particularly means.
All right, place value assigns a value to the digit depending upon its placement in a numeral. Okay, so let's take something like 3452. Okay, what do we actually mean that to represent? Well, this furthest position we refer to as the thousands position. This we refer to obviously as the hundreds. The 5 in this particular example would be the tens position, and this would be the ones position. So literally 3452 means we're looking at 3000 plus 400 plus 50 plus 2. Okay. And again, the intention behind this particular section is we're going to look at how different cultures have valued different organizational methods in representing what the numbers. Okay, so going back to that number we just looked at, 3452, which we said is 3000 plus 400 plus 50 plus 2. We also mentioned that our number system is based on base 10. So I can reevaluate each of those numbers in base 10. So the 3000, for example, would be 3 times 10 to the third power. The 400 would be 4 times 10 squared. The 50 would be 4 times 10 to the first. And then 2 would be by times 10 to the 0th power. So any of our, not just as our number system is based on position, but the position itself can be referred to as some sort of base. Just remind us that when we talk about any number to the nth power, we're saying that there's that many things that were being multiplied out in a row, that there are n factors that we're looking at. Okay, so sticking with this idea of exponents, we can actually visualize each of the positions and each of the powers of 10. So we're going to give these some different names. So 1 unit refers to one of those boxes. We're going to call one long. is equal to 10 to the first, and that's one row of 10 units. Okay, so that's got that guy right there we call one long. One flat is what we call 10 squared, and that's one row of 10 longs in both directions. So here we got, in this way we got one long, and here we have one long. Okay, and then we're going to call one block, that's going to be 10 cubed, and that's three-dimensional for us. So each of those have length one long. Okay. All right. But we can look at this to do some different types of conversions. So, question: what is the fewest number of pieces you can receive in fair exchange for 11 flats, 17 longs, and 16 units? Okay. So let's first kind of translate that into what? Okay. So we have 11 flats, 17 longs, and 16 units. And we're trying to come up with different trades that we can implement. Well, if I have 16 units, right, the 16, I can add another long, and that only leaves me with 6 units, so I can do a swap there. And so far that leaves me with 11 flats, 18 longs, and now I've got 6 units. And so the 6 is the smallest denomination that it can be. Now the 18 longs, I can swap that out for one flat, and that'll leave me with 8 longs. And so total, I would then have 12 flats, 8 longs, and 6 units. Okay, so it's just kind of like borrowing, I guess. And then from here, what else can we do? Well, remember a flat, 10 flats, I can swap out with a block. So if I add another column, one block, that'll leave me with 2 flats, still with the 8 longs, and still with the 6 units. Okay, so what would this translate into? So this would look at 1,286 would be what that number actually means. But in total number of pieces, I would have, let's see, 2 and 8's 10, 16, so I have 17 pieces total. And if you compare that to the original, in the original I had 11, 17, and 16. So I managed to get that down to a smaller collection of pieces. All right, so that brings us to different numerization systems and how we can translate into what we consider to be common numbers. So we're going to start with the tally system, tally numeration system, and this uses single strokes to represent each object that is counted. So for example, initially when they did the tally system, they didn't have the slash stroke that we're used to. They just had lines. And they would literally have to count, and this would represent, how many animals they own, how much produce they're bringing to market, stuff like that. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12. After they used this system, they actually implemented the change where every 5th unit, they put the slash in there. And so that's what we consider to be this is what we consider to be the tally systems to look like that. All right, the next culture we're going to look at is the Egyptian numeration system. This is where they used hieroglyphs to represent place value. And so you can kind of see in the chart there the different symbols they used and some of the interesting names. I would love to be in the meeting where they came up with some of those titles. The Astonished Man stands for 1,000,000. I guess if we had 1,000,000, we would be astonished. Anyways, so we're going to translate this into what we consider to be our number system. So starting with the vertical staff, we have 3 of those. Then we have 2 heel bones. We have 1 scroll. So there's the first 3 numbers, first 3 digits. Lotus flowers. Okay, so we have 1, 2, 3, 4, 5 of those. Then we have 4 pointing fingers. That's interesting. 3 pollywogs. So there's our next number. And 2 astonished men. So this would translate to 2,345,123. But there it is in Egyptian. Okay, the next culture we're going to look at is the Babylonian numeration system. See, they kind of narrow it down to 2 symbols. However, they did not use base 10. They used base 60. So in our culture, we're used to counting up to 9, and then when we get to 10, we add an extra digit. So 10 is 1, 0. Right? In the Babylonian number system, they would count up to 60, and when they got to 61, they would move over to the next place system. Okay, so let me kind of illustrate what this means, because the base is going to change what the value of it represents. So this would be, think of this as like we're adding a series of numbers together, and each space represents a different place value. So in this first one, we have in the ones position, we have 10 times 1. And then we're going to add that to this next one, which is, here we have, what is that, 551 times 60. Then we have 24, but it's 2 positions over, so it's to an exponent of 60. So 24 times 60 squared. And then 1 times 60 cubed. Okay, so I'm going to use a calculator to kind of simplify this out. Obviously, this piece is 1. 51 times 60 is something we'd actually have to calculate out. So 3,060. Then we have 24 times 60 squared. And that's 86,400. And then we have 60 cubed. And that's 216,000. Okay, so what we would have to do is we'd have to just literally add up all those